sort of the case studies that we'll dive into. I'm hoping you'll understand what are the tools in my toolbox. You know, if I'm working with a team that has a really basic foundational understanding of math and statistics, what can I show them that will really connect with them versus you're working with a really savvy team that knows their math, knows data. I can go to more advanced methods and do something more powerful. And then hopefully you'll be able to leave here and start doing your own causal analyses and sort of have that foundational knowledge to get going and learn more. Because this stuff can be very theory heavy, which is annoying. I'm going to try to avoid that. It's inevitable I have to do a little bit of that, but we're going to try to make it as practical as possible for you. So I think a really good way to kind of kick us off into the causal thinking mindset is, so a long time ago, I guess a year and a half ago, it's still kind of ongoing this debate, but people were wondering whether vitamin D supplementation, taking with supplements, I took 2 this morning, had any effect on your development of severe COVID symptoms, because vitamin D is kind of linked to the immune system and that sort of thing. So it was kind of an actual question, people say it's good for colds and such, but what if I load up every day on vitamin D? Does that mean I'm at, okay, that's just, this is a causal inference here. Oh, okay. Yeah, no, that's all good. Yeah, so people were wondering, like, if I load up on vitamin D every day, does that do anything to impact my risk of getting severe COVID? Like, you get COVID? Very natural question. And when you think about that from like a causal lens, maybe if you had everything at your disposal and you had a time machine and you could go into alternative realities and you really wanted to answer that question the best you could, like you wanted to what you have at our disposal now, you might want to take a person, like this person up here, in their observed reality, and this person started taking vitamin D really heavily on a daily basis in early 2020 when COVID started picking up, right? They took it every day. They were really diligent about it, dutiful. They lived their life, they mostly stayed indoors, but they had a friend occasionally, they got years now and then. Maybe once or twice they kind of split up and went out with that mask in 2020 or something like that, right? And then we noticed in mid-2020, they get COVID with mild symptoms, which is interesting, but that one person doesn't really, no.
It's causal.
Okay. Yeah. So they get mild COVID symptoms, but it's really just one person. I can't tell you that because this one person didn't get severe symptoms, it might even be really helps, right? It's just one person. But if we could, the most ideal way we could try to answer this question would be to take that same person in an alternative reality, also called a counterfactual reality. That's like a term from history and philosophy, meaning like the thing you don't observe in real life. And we take that person and we somehow get in there right before they start taking vitamin D, and next person will never take it. Same exact person, same demographic, same lifestyle. They make the same mistakes occasionally. They get beers with friends without a mask, and we follow them forward in time. They live their life exactly the same way, except this time we'll observe what happens. And we essentially control for every single thing except for that one factor, which is vitamin D supplementation. And now you have a really interesting contrast here. You can see, did vitamin D make a difference at all for this person? Of course, you can't do that, right? Like, you don't have access to alternative reality. That would be really nifty for us to know. So the closest thing we have are things called experiments, or A/B tests, or randomized controlled trials. Have any of you been part of an experiment, like whether it's in physics or social sciences or anything? Okay, I think I don't have to explain it that much. It's pretty intuitive, right? Like, you take a treatment group that's going to get the vitamin D supplementation, and you have a control group, and you randomize people to those groups. We follow them forward in time, and we see what happens in a few months. 6 months, I don't know, maybe 30% of the treatment group gets severe COVID, but only 20% of the control group does. Now we have that sort of difference. We can say, I think it feels like this. And it's statistically significant or something like that. So same sort of deal, we give them sugar pills versus vitamin D, and we follow them forward. The problem is, and why we can't always do experiments to see whether medication works, or whether lead exposure causes brain damage, or whether neighborhoods that have more equal income distributions have less violence or something like that. All these interesting social experiments that we want to do is they won't always save us. Sometimes experiments are not ethical, right? I can't take 1,000 pregnant people and give half of them severe lead exposure, and then the other half like nothing at all, and see like, oh, you know what, the kids do develop kind of differently, and it seems to be a problem. I mean, you can do interesting things like assign half of the group to get some sort of abatement program or something, to take lead out of their house to see if that induces some sort of benefit. But when you do tricky things like that, there's a whole set of problems with that. Also, experiments are just not feasible. If I really want to see whether income inequality is related to violence in a neighborhood, I can't take 1,000 families and ask them to move into other neighborhoods where there's like more equal income distribution. That doesn't happen. It's very logistically hard. It's not impossible. So the whole point of this tutorial session basically is what to do in these situations. You have observational data, and you really want to make a causal claim, whether it's that a product that your company is launching is going to work, or a new feature is going to work with that product, or whether, in your social science research, some question is, you want to answer that question. I keep asking these polling questions, but how many of you have prior experience at all with classic machine learning? Like nothing fancy, just sort of any machine learning? Okay, so that's more than half. One thing that was kind of helpful for me when I started this out was understanding that there's this difference between prediction, which is like classic machine learning. I want to predict something or classify something. Like this new user is going to be a power user versus a moderate one, or I don't know, like this car is going to have an issue versus not. Versus an inference type question, which is more classic statistics. And I think this is a good frame, and it kind of gets your mind in the right space to think about causal modeling. So I highly recommend this paper, by the way. This paper is incredible, and it's a little old, but it's still cool. But the thrust of it is inference questions and modeling answers questions like, what's the mean of X? Is X associated with Y? What is the strength of that association? Is it really correlated? Is it weakly? Or the causal inference question, which is, does Z cause Y in real life? Versus prediction, which we will use a little bit in this talk, but I recommend you kind of leave it by the door for now. Because what we're going to be doing is very different from prediction, which is, how can I best predict something? Between the three predictors, A, B, and C, what's the best predictor of the outcome? Or when did the model make this particular prediction, which is interpretability? So I do recommend, if you have an interest in this topic, check out this paper, really good. But yeah, so another way to think about experiments versus causal inference is sort of hierarchy of, on the far right there, you have randomized experiments, which are the best way we have right now. It's the gold standard way to figure out if something works or not, or causes something. You can make really strong causal claims with it. If I work for a company, we run a huge A/B test, and it shows our product is working, and it results in this much lift. We can go, to the press with that. We can go to our clients with that. Feel really good about that. The problem is they're not easy, like I mentioned before. Right? It's like not always feasible. It's not always ethical. If you move a little bit to the left, there is this group of methods called causal inference, which is why you're here today, which are really powerful, awesome methods. You can make causal claims with them. They're just a little bit less strong than experiments, but they're still goals. And when you can't run an experiment, the causal modeling exercise is fantastic. It's a little bit easier because you just have to work with the data you have on hand. You don't have to randomize people and follow them forward in time and do all the logistics around that. And then finally, on the far left, which is something that I think a lot of machine learning practitioners are familiar with, which is just looking at pure correlations. I have a data set. It's the Titanic data set or something, and I'm noticing there's a correlation between what class you are on the Titanic and your likelihood of passing away or something like that. That is a pure association, and there's nothing causal associated with it. It's just, that's what I saw in the data. I don't know if it's real or not, but there's an association. It's the easiest thing to do. these other things, but it's also, it provides the weakest causal claims. Some would argue even useless in terms of making causal claims. So this is a really good hierarchy to think about as you explore causal modeling. A lot of people kind of barked at me for not including, there's a mathematician and computer scientist named Jupyter who puts out this causal hierarchy that, I don't want to show you this for very long because it gets more theoretical and it's kind of complicated. But basically, this is a simplification of this. So if you carry on with this stuff, you'll find at some point, oh, there's this guy, Jupyter, he writes a lot about it, the causal hierarchy. Take a stab at looking at it and understand what it means, but basically, if you can still adapt to this. That's all. Cool, so we're going to come up on a little group exercise in a second, but is anyone familiar with causal graphs, or just graphs in general? Sort of like the nodes, the edges, yeah? Okay, half the people. For the folks that aren't familiar, this is going to be related to our first notebook exercise. Graphs are a really, really fantastic way to understand causal relationships and sort of take your domain knowledge about a topic, whether it's income inequality and some sort of public policy outcome or health outcome or some, whatever, some project you have at work, and put it on paper and show the relationships between things, and kind of understand what's really going on, what's the process that's resulting in this data, what's really going on here. So it's really simple, actually. I mean, you'll get it within 10 seconds if you haven't done this before. But essentially, each of these circles, the nodes, represent some concept or some entity or something like that. And the arrows represent a causal relationship. A is causing E. T is causing E. But B also causes D. The little bi-directional arrow at the bottom between C and D, we're not going to touch on that a lot, but sometimes you'll see that represents a pure correlation. There's no causality. D does not cause C and C does not cause D. So look at this, I'd say, okay, cool, so I have some causes and effects. It looks like E is sort of the final effect. The primary causes, the top causes are A, B, and I don't know, maybe D, I guess. And yeah, that's how you interpret it. It's kind of simple, but very helpful for this work. And I thought we could do a little group exercise to kind of wake everyone up, because I don't know about you, but I'm still really sleepy. So let's say, to get out of this mode for a second, let's say you're all working at a car insurance company or something. So we all kind of know that involves, right? And our primary task at this company is to kind of assess whether incidents are very costly in terms of medical costs versus less costly. And so let's together kind of draw out a causal graph relating all these concepts on the left to medical cost of an accident that happened yesterday. So, imagine, put on your sort of car insurance knowledge hat or whatever, if you have that. And let's try to relate some of these things to medical cost of an accident that happened recently. And some of these things on the left can cause each other. It doesn't have to be just sort of one-way connections. So I'll get started to kind of get everyone going. I think that the presence of an advanced airbag is going to be causally related to medical cost of that accident. So I think if you have a good airbag that functions well and is very advanced, you're probably going to have less injuries. That makes sense to me. So if you have any other ideas, here to shout it out. I'll add them on the screen and we can work together. What do you think?
Make and model advanced airbag.
Sorry, what's up?
Make and model relates to advanced airbag.
Okay. What do you think causes what, or where does it go here?
I think the causal relationship is from make and model to advanced airbag.
That makes so much sense. Yeah, right.
Car safety rating.
Car safety rating.
I think it probably the advanced airbag will cause a higher
yeah,
relationship.
Makes so much sense.
Yeah.
Okay. All right. So
sorry, reverse the direction of the things. The
sorry.
advanced airbag seat
you're right.
will have a higher.
Thank you so much.
Yeah.
So like this thing you're saying?
Yes.
That makes sense. Yeah. The opposite doesn't make sense. Cool. What else do you think? I mean, I don't know how an insurance company would get a person's risk aversion, but look, I don't know, maybe there's some crazy advanced car insurance company and they have that information for some reason. I don't know. What else do you think? Just feel free to shout them out.
Say if they took a driving course, that probably affects an estimate of the risk aversion.
Okay, cool. I like that. How should these things be
The driving
related?
course to your risk aversion.
Driving course to risk aversion. Okay. So you think taking a driving course will make you less risk averse? But the idea?
More and more.
Or being risk averse will make you more likely to take a driving course. Yeah, I don't know. Interesting. Yeah, I mean, we could make this bi-directional, I guess. That's always a thing. These
But
things-
causality is never bidirectional, right?
What's that?
Causality, can that be bidirectional?
It can. So, for instance, physical activity and depression have a bi-directional causal relationship. You know, if you do less exercise, you're more likely to be depressed. If you are depressed, you're less likely to exercise. But we won't be talking about too much about that. It's kind of complex. But yeah, that's a good question. Very good question. How does this relate to the medical cost, do you think? Is this like both of these directly causally relate to the outcome? I think so. Yeah, I think so. If you're risk averse, you're not going to drive super fast. Makes sense. So I'm going to draw that in here. Okay. Cool. I think you get the gist of it though. So the point is of this exercise is we can draw a causal graph. We did it with our domain knowledge. There's no data involved. And that's something that is really important in causal modeling is you have to sort of know the domain. You have to know what generates the data and what's going on in real life. A lot of people say causal modeling is sort of machine learning plus domain knowledge, or deeper domain knowledge, essentially. Oh, question or no? Gretchen? Yes, question. Cool. Okay. So we're getting to that exercise. It'll happen a little bit, but we're going to start talking now about the 4 types of causal relationships that are come up again and again that are related to graphs. Because, you know, if we can draw a graph like this, we can kind of talk through like, this is an interesting little piece here. We got to watch out for this. This is the problem. So there are things to look out for with causal inference. You have to sort of avoid traps. So let's say you are the mayor of a big city, a million people live in that, and you have a big crime problem, violent crime particularly. And so you're a responsible mayor, you're 21st century mayor, so you say, I want to see the data, I want to see what's going on here. So you have some analysts that brings you data and they say, hey, we've got a really strong correlation between ice cream sales and violent crime. I think we got to do something with ice cream sales right now. Does that make sense?
Yes.
Yeah? Yeah. It does not make sense. But it's such a strong correlation, and you can't ignore it, right? There's going to be something there. Probably this is a kind of a canonical confounding example here, and we're going to hear about confounding a lot. The problem is there's actually a causal relationship between hot weather, this third variable, which causes ice cream sales, that causes violent crime. Both of these things are in temperature, these are the real things. You know, if you have more opportunities for violent crime when the weather is good, and also kind of crazy epidemiology findings, hotter weather induces more like rage and violence in people. I think in baseball games or something like that, when days are hotter, pitchers are more likely to hit batters or something like that. That's the example that they caused. So with confounding, what's happening here is the fact that hot weather is causally related to ice cream sales and violent crime. That sort of splitting there induces a fake relationship between ice cream sales and violent crime. That's a no. We want to avoid that. So we're going to spend a lot of time trying to figure out what's going on with confounding in this data set or this problem, and we're going to try to untangle these things and create the confounding. So So how do you fix this? I mean, you might say, hey, nice data set you brought me, nice correlation, but that's BS. That's not what's going on here. I want you to update your analysis and sort of get back to me what you think is the root cause. So what we do is you control for this hot weather confounder, this third variable. And once you do that, the association between ice cream sales and violent crime goes away. It is no longer a problem. You control for confounding, which is what you'll be doing in 80% of causal modeling. It's basically identifying with your domain knowledge what could be a confounder and what's the most appropriate way to control for that confounder so I can really understand what the deal is between ice cream sales and violent crime. Why am I seeing that bogus association? And so one of the four big causal relationships to watch out for is confounding. Another sort of canonical example they teach people in epidemiology 101 is if you look at any public data set where people provide information on their coffee consumption and you have information on their medical records as to whether they have lung cancer, you will find a moderate association between coffee consumption and lung cancer every single time. Which turns out is completely bogus. There is no biological mechanism that can relate coffee consumption to the risk of getting cancer. They study that extensively. If anything, it's the opposite, because coffee has some antioxidant properties. So what's going on? The problem is smoking. I double checked this the other day. It's actually causally related to coffee consumption. Like you are more likely to consume coffee if you smoke, which I wanted to double check, but it's a real thing actually, turns out. It's not a correlation. And so smoking is the confounder here. It's causing coffee consumption and it causes lung cancer. And so you see this kind of bogus association in your data set, your observational data set between coffee and lung cancer. Shouldn't be there. So what you need to do is control for smoking in any sort of study where you want to see what's the relationship between coffee and lung cancer. Confounding can be very damaging to analyses. It can change the direction of the association between two things. There's truly no relationship between coffee and lung cancer, but you might find in your observational data there's a strong direct association, where coffee is highly correlated with lung cancer. Or you might find the opposite. You might find coffee has a strong protective effect, like super protective. Like we should all be drinking coffee constantly, we'll never get cancer ever, which doesn't make sense. And so it's a big problem, and a model will ideally control for confounders like this. But if it doesn't, this is a little bit of Lego here. Any leftover confounding, like if there are other confounders kind of messing up the association between coffee and lung cancer, we call that residual confounding, like leftover confounding after you try to control it for things.
Question. Yeah. So how do you come up with that? That you did it a few minutes ago. So you have to have some domain knowledge and then encode it in the graph.
Yeah, you have to have some domain knowledge. You have to kind of. This is what makes causal modeling and inference, I think, more challenging than machine learning. Frankly, you have to have really good domain knowledge. You sort of observe, like there is this association, it seems, between coffee and smoking. I wonder if it's causal. We have data on that. That's awesome. I don't think it's anything but a confounder. Let's try to control for it and see what happens. And we do that. It's a lot of domain knowledge. Yeah.
But I mean, I think domain knowledge should be really important in machine learning too, right? It's just to be able to know what questions to ask and what questions not to ask.
That's very true.
That's an interesting question.
Yeah, that's a good point. I guess the difference is with machine learning, domain knowledge is really key, and it helps you sort of identify the predictors. Like, based on this, I think we're going to make this feature and that feature, or something like that. With causal inference, as we're going to find out later on, you don't ever want to put all your variables into the model to sort of control for them. Controlling for some things is actually harmful. We're going to do the next entity we look at, actually. So you have to sort of be a bit discriminating. And more lingo, we call, I don't know if this is necessary really, but we call a situation where a confounder pushes the association from 0 outward to positive confounding versus negative confounding, where it kind of shrinks the real. Yeah.
So go back to the previous slide.
Sure.
So we talked about kind of the leftover confounding, is called the residual confounding. That sounds kind of like it's analogous to like epistemic uncertainty in machine learning. Like you don't really know like your full model
I guess I'm not too familiar with that term. Can you describe
It's
that?
kind of like a bias, right? So you would have like things related to just the stochastic statistics of something versus like missing information, missing domain knowledge in your model. So how do you quantify that? What are we going to get?
I guess so. So it can come up in a few ways. So one is, let's say coffee is a simple 1 or 0 in your data. It's a binary variable. And lung cancer is a simple binary 1 or 0. And you have a choice between controlling for smoking, which is either a 1 or 0 or a continuous variable, which you can sort of handle non-linearly in interesting ways. Oftentimes, if you control for smoking as a binary variable, you'll have residual confounding because you haven't done if you sort of lose information in the identification of smoking. Whereas if you were to use a causal model that we'll get into later on and it was sort of continuous, maybe you can account for more nonlinearity and interesting sort of confounding effects. That's one residual confounding. Or, if you identify smoking and some other confounders of this association, but you leave a few out, that's also residual confounding. I'm not sure, maybe that is sort of what you're talking about.
Right, so it's kind of like, how do you detect that you have like an unacceptable amount of residual confounding, and how do you correct for that? Or how do you decide, like, how do you go get more domain knowledge?
Oh, I see. So that's what makes causal inference really hard. There is no ground truth. If I want to understand the association between coffee and lung cancer, I'm not really going to find any ground truth data or thing in the real world that says, no, there really should be an association and it should be 0.5 or something like that. With machine learning, I can make a model that predicts something, and I can tell you repeatedly it predicts an 80% accuracy in many different test sets of data it hasn't seen. And so I can be reasonably sure that it's going to perform that well. And I know how it performs on unseen data. With causal inference, it's just, is your domain knowledge good? Is your data good? You have to take the best swing at it. I think that's what makes this a lot harder than machine learning, honestly. Yeah. Okay, so another quantity number 2, or causal relationship number 2, is called a collider. It looks similar, but it's a little different. Look, so in this case here, the arrows are going from the 2 to 1. You have a common effect. A little different than this. The arrows are going the other way. You never want to control for a collider. It will induce bias. So in this case here, if you want to understand the association between smoking and lung cancer, and you happen to have a data set that has those quantities, and you also have numbers of sick days taken, you might think, cool, I'll just control for that. Throw it in the model. I like to run stuff in the model. You will bias your association between smoking and lung cancer. You never want to control for a common effect. This bias is called collider bias. I think it's also called M bias. It can be negative or positive. I can't really tell you which way it'll go. It just depends on the data, but it's something to watch out for. And the only way you can really know this is through your domain knowledge. It's sort of saying, hey, wait a second, I have numbers of sick days taken, smoking and numbers of sick days taken. They should be causally related, and lung cancer will cause you to have more sick days taken. So I don't want to control for that. You just have to deploy your domain knowledge. That's really no other way. Does that make sense? The difference between this and this? Okay. The third one is called mediation, which I think is really intuitive, which is when you have a variable which is sort of in the middle of a pathway between causal pathway between 2 things. If I want to understand the relationship between smoking and lung cancer, and I have some data on clinical signs of lung damage, which is sort of between the two, if I control for that, the association between smoking and lung cancer goes completely away because I've blocked the pathway. If that makes sense. If I shoot out that little variable there's no connection between smoking and lung cancer. Presumably, I don't think there's another method or way that can happen. Yeah.
Can you explain what you practically mean by control for? Like, how does that manifest in an experiment?
Yeah, sorry. I should have introduced that earlier, maybe. So there are a few ways to control for it. One is you can control for things with a model, which we'll do some modeling in a little bit, and exercises 2, 3, 4, 5. So these are actually the models we can use where we throw it in, and it will do the magic for us. You can also do really basic things like if you have a data set and the variable you want to control is like a 1 or a 0, it's like a binary, if you sort of filter out all the zeros, so it's only one, there's no variability in that variable and it's controlled for. That's called stratifying on it. So, in the absence of any modeling techniques, to just force that variable you want to control to be just one value. And if there's no variability, it can't exert effect. Yeah, that makes sense. Problem with that though is you lose data set, right? Sample size of that. Does this make sense? Sort of mediation relationship? Okay. And then the last one, which I guess is less of a concern, is just unrelated filters. So if I want to understand smoking and whether it causes lung cancer, and I have some third variable which causes lung cancer, and that's it, it's just sort of a single pathway. There's no problem with leaving it in, controlling for it, doesn't really matter. I mean, it's not going to hurt things. Yeah. That would be different though if there was a causal arrow between, let's see here. No, not really. Yeah, if there's just a single pathway between that third variable and the outcome, it's not a problem. It's all good. Yeah.
So wouldn't this still kind of affect the effect size for smoking?
Sorry, what's that?
Wouldn't that leaving out the other variable affect effect size of smoking?
It would if there was a causal arrow from here to here. Then it would be a confounder, that first relationship we talked about. But because there's really only one pathway here, and this is the only relationship, then it's, leave it in, control for it, doesn't really matter. Yeah. This can be really confusing, actually. Does this make sense, these four relationships? I can take a break and we can sort of talk through specific ones more closely if that would be helpful. It took me a while to understand these four things in school. Makes sense. Yeah, okay. Now, of course, the real world is really complicated. And so if you do embark in these exercises, you're going to find you're on a whiteboard somewhere drawing out things like this. It gets really complicated. But it's important to do these things because if I were to just sort of say, I want to see if smoking has an effect on lung cancer, and you toss all these things into the model, you're going to be controlling for mediators, you're going to be controlling for confounders, which is good, you'll be controlling for colliders. Some of that's bad. So you have to sort of think through what's going on here to the best of your ability. Work with domain experts, learn it yourself, and try to kind of piece it apart. Because this is probably closer to reality. If you have like 8 variables or entities, then you'll have all these different arrows going between them. It can get complicated quick, but it's important to do this stuff. I mean, I think the best advice I can give, honestly, is sit down, take stock of what variables you have, like what data you have, and then talk with your domain expert and try to figure out what do you think are really key variables to think about? Like, let's just focus on 4 of these covariates and sort of think through what they could be causing and what their relationship is, as opposed to let's bring a data set in with 100 covariates and sit down for a few days and really get into this. That's kind of a losing proposition, I think. So we're about to take a break for that first exercise. One sort of final summary is experiments or A/B tests are really awesome because the act of randomization between some treatment, like treatment and control, breaks all confounding. That's why they're so valued. They're awesome. If I'm randomizing half the room over here to take some real pill and this half to take a sugar pill, all of your demographics and all of your attributes are no longer causally related to the treatment status. You're randomized. And so you've broken all that confounding, and you can make an awesome, easy causal claim from that. With causal inference, the task is to take observational data and think through the domain knowledge and try to construct something like this and sort of think through, do I control for that, do I not? And if you can do that, that's when the magic happens and you can make really great causal claims for things. So the first notebook exercise requires RapidViz, which unfortunately I heard some folks were not able to install. If you're not able to install it, don't worry. I think you can still use a lot of the notebook, but I would look at the teacher notebook, which has some of those plots in it. Basically we're going to be generating synthetic data, simulation data that covers the four relationships: confounding, collider bias, mediation, and unrelated predictors. And just sort of verifying for ourselves that, okay, I have a confounder here. If I leave it in, what's the association? If I control for it, does that change? So that's what you'll be doing. It's in one student causal graphs Python notebook. So yeah, I'll walk around. Let me know if you have any questions or anything, and probably spend like 15, 20 minutes on this and see where we're at. And feel free to work in groups if you want, or work individually. Whatever you're comfortable with. Yeah.
I have one more question for the last slide. When you said in your advice that you would like to only, care about 4 of these things and then really figure those out, aren't you prone to accidentally, control for colliders, for instance? When do you not have to work out all the relationships?
I guess that last part. Are you prone to
not control for colliders then, if you don't, take into account all the other things that
it's a risk. It's a risk. I guess the best you can really do is sort of take stock of the variables you do have and just try to make an honest effort at capturing the really important ones in your mind, like the biggest confounders. And I mean, honestly, that is the best you can do. If you're doing it rigorously with domain knowledge, then take an honest stab at it. Honestly, that's the truth. I think a lot of the way people treat this stuff is a few causal inference modeling exercises are as valuable as one experiment. So, if you do a bunch of this work over time, you might see the preponderance of evidence suggests there is this causal relationship, and I really believe it now after a few different exercises. And you sort of get at the truth that way. But yeah, so there's no access to the truth with a capital T that I can look up to see is the answer correct? Yeah.
The experiment is the only verification then, right?
It's the best way we have. It'll probably be the best way we ever have, unless we can access the multiverse or something. Yeah, it's just unfortunate. So I guess everyone should have access to the repo, right? But this is essentially what you'll be working on. So yeah, give it a shot. Let me know what you think. I'll be walking around.
So other than time, is there any cost to doing different, experiments with your data, sort of saying let's store this thing in here and see if it doesn't any bad, and then take it out and then put another one. I mean, is that a good idea or a bad idea?
Yeah, I think that can be a useful extent of playing with the percent it's strong. That can happen for a few reasons. It could be because it's a mediator, and I shouldn't be doing that. Or it could also be it's a confounder, and that's an expected reduction. But it's hard. Again, you sort of have to rely on that domain knowledge to sort of understand that. It's going to be frustrating for people. No one's having a hard time with the code. Yeah. I sure did. Yeah. And it comes with so if I don't control it, I have these two variables in my data set. And from a simple correlation, that's the big one. I'll find it really strong. It should be that's not a possible yeah, totally. There's something that it's Yeah, there's a really cool website, I think, that shows you like all the correlations are. Number of elements, and how many birds are flying this season, something like that. It's all concocted stuff. So you want to control this. You want to control it. I think choose this question. The same question. Use it as a model. Yeah. So there are 2 ways to do it. One is through actual machine learning type model that would do it. The other way, which is in the first approach, is to simply stratify each of them. You know, if you have a data set that only show me exactly only show me people from the data set because this is no longer it's sort of tutorial, you know. And it can be not smoke or smoke. Either way, it's one that's and you see it. You see only the people that smoke correlation between functions and non-answer functions. But if you have smoke that variability between 0 and 1 so this is what okay, to very close point something but I never want to say looks like we want to have this stratify. But there's a lot of things that are so much so just I guess the bigger picture would be you're working on a study and you want to you can't find a relationship between levels. I want to have the observational data. I can't do an experiment. And if I look at the raw associations, there will be one here. I'm not sure about whether it's possible. It's a correlation. So then you might work with someone who says, I'm going to talk to you about something well, sort of figure around who wants to go to and we also have I think it's you'd be wrong. It could make it go to 0. It could make it much stronger than there should be. For example, yeah, this is it. Let's say we have relationships. And we also have a third variable, which is, say, I want to quantify the degree of, so we have to study the level, or something like that. This is how they launch that. They launch control this by trying to look at people with severe lung damage, or no lung damage at all, or if I throw this into the causal model, which I'll show you. This association, taken out the time. That makes sense. There's no way these two can connect each other causally. That makes sense. Yeah, let me take this one.
What about like farming or something?
Yeah. I guess it's another thing is three variables of each other interaction. Anything like that, we can use that in software. Okay. You take some medication. Taking that medication results in some side effect. And that side effect I don't know, like, not only the house, there is a causal relationship between taking that medication and the body control for the jittering. No longer see association. And knowing these scores, even yes, so systems like that. I think so, yeah. So it's like, yes, actually something like that. They're actually called the structure. Even that data set, people draw based on sort of that changes this. So testing if you do that, you will have a result that yeah, you can basically simulate experiments. Machine learning association. Yes. Yeah, exactly. We'll talk about it. variable. And they share this relative.
Yeah, that's essentially.
So you're like, really work in terms of that outcome process. That's yeah. Oh, okay. So they're not having trouble with You'll only ever need that for the first exercise, and after that, we're fine. Cool.
Whether there's a confounding relationship, whether it's a lining relationship, whether it's a mediating relationship, that's something intuitively that not clear.
That's a great question. There are algorithms designed to feed in data and will try to create a graph for you. I have a slide on that for you. I think, to be honest with you, I think it's like useful, but people tend to like put full faith in it. I think if you're not using any domain, it's going to be used. But it's helpful, yeah. I've done that before. Like I had 30 variables I ran through and I estimated the graph. Yeah, put that in. No. Yeah.
Maybe it's wrong.
Yeah.
So, sorry. So, basically, instead of all stuff, maybe in the second exercise, you lead us to step through the exercise. So,
Okay, yeah, I'll do that.
yeah, that's I guess I'm not even like that a lot. People are not interested in stuff.
Okay, yeah, thanks. Sorry, what was your name?
Oliver.
Oliver. Hey everyone, Oliver just pointed out to me, it might be helpful if I walk through that first note, but just sort of high level, like this is what's happening here. Is that, okay, yeah, sorry about that. Talk about the, zoom in here a little bit. Okay, so what you're doing here is, we're looking closer at those four causal relationships and sort of play with the data and see what they do with the real data as opposed to theoretical. So, in this first one here, we're looking at classic confounding. We're going to use this cool library that you're able to sort of like direct what the relationships are between things and simulate data. It's really neat actually, you can sort of test it. In this case here, what we're doing is looking at smoking, coffee, and lung cancer, a classic confounding example we looked at in the slide. And I'm saying, you know, in this case here, the true causal relationship is smoking is causing coffee consumption, and smoking is causing lung cancer risk. So it's sort of like this. I'm basically encoding that in that package. And then once I have that, I can draw it. Then we have
The linear model means it's a linear relationship, right?
yeah, exactly. And then I can draw samples from it, like real synthetic data. You will have a pandas data frame done on your front, which is really cool. And then, you know, once you have that pandas data frame created, you can start looking at correlations between some of these things. So this is a Spearman, a Pearson correlation. And I want to see what it is between coffee and lung cancer risk. And I can draw it out, I can plot it. And then what I'm doing here is I'm saying, what we talked about earlier, like there's two ways to control for a variable. You can throw it into a model, which we will do in the next exercises, but for this one, the really basic way you can control for something is just force it to take on one value, like filter it. If there's no variability in that, it doesn't exert any effect in your data. So I'm saying force smoking to be just 0 in this data set, like look at that subset, and look at that correlation again, and you will find that it changes the correlation. You control it for confounding. And you'll find that there is no longer any association between coffee and lung cancer. And with the rest of the exercise, you kind of like that, so it's similar workflow. You kind of encode the relationship to look like this. Generate data, control for that third variable, and see what happens to the association. So that's all it is. Does that make sense?
The second variable in your linear model, that's weight, right? So is that just like a factor that gets multiplied?
Oh, yeah, that's it's sort of like a beta coefficient or something. It's like a weight, yeah, exactly. You can change that. It doesn't have to be 1.5 or 6, because you have to specify something. So
Okay.
yeah, that's a good point.
It doesn't mean anything, and then we work this example just like the execution.
Let me actually take this off. I'm sorry, it might be easier to walk through this.
So I guess my question is like, if the coefficient's larger, does that mean a strong correlation or?
It can be, yeah. If you change those coefficients, you can have stronger confounding, weaker confounding. You'll still see some confounding if the basic relationships are like this, but it still change the magnitude, yeah. Create a pandas data frame that includes that. I want to see how is coffee consumption correlated with lung cancer. There should be not, because coffee does not cause lung cancer or protect strongly against it. Strongly. And I find that they're directly causally related, like moderately strong. So if I was to naively look at this, I would say, oh my God, coffee causes cancer. I'm going to do something about this. But if I take this data set and I force everyone, there's ones and zeros in the smoking column. If I force everyone to be a 0 in smoking, I've stratified on it, I've filtered on it, the correlation completely vanishes. You've controlled for confounding smoking. This is basically like the 0 correlation, completely gone. So you'll explore here, like if I control for a collider, you'll see that it induces bias. And if you control for a mediator, you'll see that it completely nullifies the effect between your variable of interest and outcome. And you'll see, if this is like not enough information to work out, but look at the teacher notebook, and you'll find that when you create an unrelated predictor, like in here, controlling for it does nothing at all. It's just, you can do it if you want, you don't have to do it, it doesn't really matter. So I guess I would say like refer to these slides here back and forth to understand what's going on with these 4 sections here.
Can you briefly say how the weight argument works in like model creation?
Yeah, sure. So I think it just determines sort of the strength of the sort of encoded relationship between these things. So like in this case here, if I change this to 6 or like 10 or 100, I mean, all it's going to do is sort of change the strength of the confounding a bit. The confounding will still exist. So I don't know, you'll see slightly different correlations at the end, but you'll still basically see this thing of like my control for confounding. Coffee is in no way associated with lung cancer as it should be. I probably should have made that clear in the notebook actually. Yeah.
Oh, and
They're completely arbitrary, so these numbers here.
got it. When you put 2 variables as the first argument into the logistic model, it means that it's going to be correlated with both.
Yeah.
Like in the example of there's diabetes being correlated with both.
What I'm doing here is I'm saying, generate a smoking variable, which is 1 or 0, where 1 happens 30% of the time. and generate like some number of samples of it. For coffee, I'm saying, I want you to force smoking to cause coffee consumption. And I want that magnitude of that forcing to be 1.5, whatever that means. You can make it 350, 22, whatever. And I'm saying here, force this new variable lung cancer risk to be arise from smoking. So you get this again. It's kind of cool in a sense. I mean, you can construct like you can use that to construct listics. If you intersect and represent this with that same technique, you just keep adding lines here and get, make this one related to that one, and then you can just simulate that data and experiment with it. Thanks. Yeah. It's not good. I'm going to actually show really quick what you talked about, just to make it clear. In the collider example, I'm sorry, I forget your name. Anna. Okay. Anna had mentioned, hey, I'm doing this, and I'm noticing, cool, there is no correlation between household income and your genetic risk of diabetes, which makes sense. But if I control for that collider, if I control for that collider, I see it's like a very, very minor bias it produces. Like it's still basically a zero correlation. You can change that by making this stronger. These beta coefficients are much stronger. If you make that like 20 and 15, negative 15, you'll see that, oh my god, there's this crazy amount of collider bias if I control for the collider. So feel free to give that a shot. Like play with these coefficients here, and you'll see it has a huge effect. So. Okay, is everyone making progress? So we should do all the rest of it? Start with it. Any objections? Okay, I'm going to keep moving on. I'll say this, the exercises are kind of backloaded in this tutorial, so thus far it's been a lot of me talking, but increasingly it'll be like talking 3 minutes, new exercise, talking 5 minutes, new exercise, as opposed to me like that right now. So, real quick, I had this conversation with Ian. Yes. Okay. Really important. Like, I would love if you all took this away from this talk. There's this sort of impression out there that in machine learning, variable importance plots tell you about what's going on with like, the data. Like, in this case here, if I was predicting, I don't know, this would be like, I guess this is Titanic, it looks like it. The likelihood of someone to pass away in Titanic, I might say, oh my god, I think tidal is causally related to that. I think something really important is going on there. Taking class 2, I get too. These variable importance plots that you see in machine learning tell you nothing at all about causal relationships. So when I think about these, I think about sort of helping you understand what variables strongly predict versus less strongly predict, but it doesn't tell you about what's causing what at all. So beware of that. There's sort of a misunderstanding out there that like these plots will tell you about the data generating mechanism and what's really going on. That is not true at all. So beware. This is prediction, and we're doing inference. Okay, so I think I touched on this a little bit earlier, but I guess my high-level recommendation would be when you want to do a causal inference exercise to see if two things are causally related. I would first sit down and think through domain knowledge, bring in domain experts, talk through them, maybe do some whiteboarding with them, sort of like draw the nodes and causal relationships, and like understand what's going on perhaps. And I would pick a small subset of variables that you know you have data on, and then you sort of think will exert a big effect, like frivolous. Before you do any modeling work, which we're going to do in the next exercise, we're not going to do the sort of simplistic stuff we did in the first exercise. Look at bivariate relationships. Try to understand for yourself this variable and this variable. Is there any correlation there, positive, negative, or not? What about these two? What about these two? That sort of gives you a sense for like what could be going on and what traps you could be falling into. And then, of course, identify the confounders if you can, and avoid controlling for things that you shouldn't control for, i.e. colliders and mediators. Someone else asked a really interesting question. Actually, someone asked, this seems like I could possibly automate this stuff. Like if I feed in a data set with 100 columns in it, it seems like I could generate some rules or some algorithm that sort of say, I think these are causally related based on like, I control for that, this vanishes. I control for that, this one vanishes. So they do exist. I would say just be very cautious. I use them sometimes, but I always, domain knowledge has veto power over them. So like I'll run it, I'll get a graph that comes out of it. There's a lot of interesting research around it, but always rely on domain knowledge versus the empirical stuff. I think it can be a bit of a WMD if you don't really think about domain stuff and just run it through. In fact, I don't, I'm not going to say that. But this is an interesting fact. When you use those approaches to sort of, they call it causal structure learning, to learn like what were the nodes and the lines there, it can be really tricky. So for instance, these three graphs here belong to the same thing, this Markov equivalence class. They are completely indistinguishable if I only have 3 columns of data and I have no domain knowledge as to what could be causing what. I throw it into one of these algorithms, completely indistinguishable. For this stuff up here, I had to know, I strongly suspect that smoking is, clinical signs of lung damage is not a confounder. I think it's causally related to these this way. I rely on my domain knowledge. I think that this is a collider. I think this is a confounder. That's the domain knowledge piece. If I just throw these into an approach to learn structured graph, causal graph automatically, you can't trust that at all. These are completely indistinguishable. Interestingly, if you have 50 nodes, or a lot more variables, it actually becomes easier to determine the structure because you can rely on sort of more variables to bounce each other off and sort of make comparisons. But when it's 3, you can't tell anything. It's kind of funny.
Question from,
Yeah.
if you, there's ways of like you give the structure, and you just want the system to learn like the amount of inference. Would you still say that's not a good idea? If you gave it the structure and just say, give that data, can you learn like how big the influence is? Would you still say that's a bad idea? Or
No, that's fair game. Yeah, if you're confident about the causal graph and what causes what,
yes,
there's tons of techniques to feed in data and sort of estimate the relationships and the strength of causal matches. Yeah, that's fair. Okay. It's just learning this from pure data and zero domain knowledge is a big no-no. I would avoid that. Okay, really quick aside here, if any of y'all are interested in bias and fairness and sort of topic of it, there's a cool tie-in to this, which is, nowadays we know that black box models are awful for modeling like crime or who gets a credit card or, what job application should be looked at more closely. Causal modeling offers you a really interesting way to sort of describe the relationships in data and think through where bias could be coming in and causing damage in a nice visual framework. So there's this well-known case from the 70s of sex bias that occurred at Berkeley. Sort of a debate whether or not it actually happened or not. It's a really interesting case actually if you look into it a little deeper. But causal graphs, like the kind we just worked on, offer you a really nice way to sort of understand what could be going on in the data. There's a really cool Google DeepMind post by Sylvia Chiappa where she explores gender and how it influences department admissions at Berkeley. A really, really cool article. I highly recommend it if you're interested in this stuff. Cool. Okay, another group exercise. So we talked through the 4 causal relationships. We're going to be getting very, very soon to actually modeling work, something kind of closer to like sklearn with causal inference, which is cool and much easier than the first one, I think. But we have to talk through some of the assumptions of causal inference. Turns out you can't just like, throw that data willy-nilly. You have to also, beyond domain knowledge, you have to sort of think through are my assumptions met or not, because there are technical assumptions. So first assumption is, when I'm doing causal inference work, is temporality. Causes always occur before effects. And so if in your data set, you want to see whether some variable has an effect on another variable, and the outcome occurred before the thing you want to see if it had an effect, causal inference does not work for you. It will provide bogus results. I would not trust it at all. You have to ensure that, as you've drawn this out, are causes actually occurring before effects in the data generating process. You have to, there's an assumption called stable unit treatment. It's a really pretentious thing. Basically, it means you want to make sure in your data set, each row doesn't exert an influence on another row. So in the case of like smoking, coffee, and lung cancer, if for some reason patients cluster a certain way and like influence the coffee consumption behavior of other people, it throws causal inference out the window. You can't trust those results. You have to assume every individual is completely unique snowflake and they're unrelated to each other, which can be challenging, like especially if you do causal inference work with like social media stuff. Because people talk to each other and exert influence. There's something called causativity, which means you have to make sure you have enough data so that within each of your covariates you're controlling for, are there enough outcome values one way or the other? Are there enough treatment values one way or the other? Yeah.
Maybe I should let you finish.
Okay. If you don't have positivity, and for instance, you want to control for a confounder, but in your small data set, you only have folks that like received the treatment and know that none of them didn't receive the treatment, and you try to control for that confounder, like it's going to cause bias or wrong estimates essentially. So you have to have enough data. There has to be enough variability in the data to make good causal inference. And then finally, the big one, which is, this happens quite often, honestly, ignorability, which is you have to account for all major confounding variables. If your data doesn't have critical confounding variables, you're not going to be able to do a really good job controlling for them, and you'll have bias in your estimates. So, I don't know, I would say bring in your domain experts, see if the key variables you need are in the data, and if they're not, then I don't know, maybe consider whether it's feasible to run an experiment and sort of control for confounding that way and come up with better estimates. But you have to have the right kinds of data, otherwise this doesn't work well. Yeah.
So for bidirectional causality, then your data set needs some kind of time measurement there, right? To be able to. You say causes occur before effects, and then you have a bidirectional causality.
That can be really tricky. Yeah, exactly. Yeah. That can throw things off, yeah. So I would say if you have the slides open, kind of keep them on this page on your screens, and for the next few exercises, we're going to shout out what you think, what assumptions are being not met. So like, keep this open. Temporality, positivity, and ignorability. And here's some example studies. I want you to sort of shout out what you think assumptions being violated. Okay, I want to understand whether frequent emails to customers could impact customer satisfaction. That makes sense. I have survey data from customers and self-reported satisfaction from a year ago. And I'm going to use this month's number of emails written to that customer as sort of a proxy for how much we generate emails. So I have an outcome from a year ago that I'm going to sort of use as a proxy for satisfaction. And I'm going to use this month's number of emails we wrote to the customers as a sense for like how often do we write them generally. What do you think was violated here? Temporality. Yep, you got it. What about this one? I want to see the causal impact of a neighborhood's cleanliness, sort of broken glass theory, whatever it's called, on crime rates. And so I want to control for something like 20 confounders. The problem is my data set only has like 10 neighborhoods in it, and the unit of analysis is a neighborhood. I'm not looking at people, I'm looking at like each row corresponds to a unique neighborhood. So my sample size is effectively 40. Can I do this?
Positivity is hard.
What's that?
Positivity is hard.
Positivity, yeah. There's no way you have enough variability across 20 covariates, across 20 strata of covariates to account for like, clean neighborhood versus not clean neighborhood, high crime versus not crime. It's just, there's no way there's that variability in each column essentially. So this is bogus. What about this one? I'm working at a company, we're gonna release a new multiplayer game through some social media app. And I want to see if like this game, this app impacts user engagement. I want to see if like the presence of the game makes people more engaged. And so the problem here though is when I ran this analysis, some users have played the game, some have not. And because it's a social media app, users can sort of talk to each other and say like, hey, this is a cool game, I would check it out, and sort of influence each other's exposure to the game. What's wrong with that? Yeah, exactly. The second one. Yeah. The treatment status, whether someone played a game or not, can influence the outcomes of other individuals. So they can talk to each other, they can sort of network. We don't have that sort of isolation of individuals in society. And the last one, which I guess is through process of elimination, we can guess, is we have a job training program. We want to see how it can impact someone's future income. Unfortunately, we don't have a ton of data on participants, so essentially we're just going to control privilege to see if there's a causal relationship between doing the program and income. One confounder. For the last one, because there's probably tons of confounders, like what your demographics are, where you're from, what kind of job you have. Just controlling for age is not going to be enough. So that's violated for sure. Okay, so now we're going to get into like modeling, which I think is going to be more interesting than the first one. So we're going to go over a few different types of models for the rest of the tutorial. And it kind of follows a similar sort of pattern as that earlier hierarchy I showed you, where you have like trade-offs you can make between approaches. On the far left is probably the most interpretable and the commonly used approach. You see it everywhere, like in the literature and the companies. It's known as propensity score matching, or PSM. It provides very interpretable results. It's very easy to understand for like different teams and stakeholders or in studies. But it is a little bit less complex than other methods, and there's some discussion as to whether it does all it can do to control for confounding and stuff. A little bit over, you have something very pretentious name, you have this g-computation or g-comp. And it is a bit more complex than PSM. It uses machine learning at the heart of it. And there are some studies that suggest that it is better than PSM at controlling for confounding. It gives you good causal estimates. And then at the end, there are more recent methods like double ML, which we might have time to get into, but same sort of pattern there, more complex, less interpretable. As I mentioned, like the jury is still out as to like which of these. I think this is sort of like the increasingly understood hierarchy of like power, like double ML, more powerful than g-comp, more powerful than PSM. But the jury is still out. People are running simulation studies and trying to understand what's the best way to do it. I think for now, I would just trust this hierarchy. Okay, so we're going to be doing PSM on the first exercise, but I wanted to sort of return to this idea of counterfactuals. So we have an observed reality from the very beginning, which is we have someone that smokes, and we have the alternative reality where everything about that individual is the same except they don't smoke. let's say we're working with a binary treatment. Binary treatment, smoke versus not smoke. And the outcome of interest is their systolic blood pressure. There's a relationship between these two. Like smoking kind of messes up your blood pressure. To really understand the causal model approach, like what the impact of smoking is, essentially I'm going to model the smoking status, what we observe, and the counterfactual of not smoking, and hold everything else constant, and see what that delta is in the outcome. And that delta is essentially going to be the treatment effect. That's what's of interest, you know? So from there, I could say, I know smoking has this delta associated with it, has this effect. And essentially we just want to exercise to then do this for groups of people. We'll have some people that have some treatment of interest, some policy of interest. You know, maybe like they're not smokers versus smokers. We'll see what the mean outcome is in those two groups and what that average treatment effect. Which you see here, these are some of the most common causal inference metrics that people report. So this top one is the average treatment effect among the entire population. You can also look at like just among the people that received some treatment, what was the effect that we saw there. You can look at it through a number of different lenses. So propensity score. Okay, so we have some treatment. That's the treatment column. And we have some outcomes. It doesn't really matter what it is. Like let's say like some risk for corresponds to like one factor. We have some filters. So we're going to start with something like this. Let's have what we're going to do is for each individual in this data set, we're going to use a machine learning model. It doesn't matter what it is. It can be something really simple, maybe something really simple, something really complex, doesn't really matter. And for each individual, we're going to essentially predict treatment status from the filter. And these are probabilities of the parameter, which corresponds to individual markers. So the first up here, item number 1. For whatever reason, we're not having to be out but people can't their attributes. They were more likely than not to receive the treatment. Maybe for given their age, whether their income, or some attributes about them. We just think the model predicts they're highly likely to get a treatment value of 1 to receive the treatment. And it varies among the population. ID number 5 here. Given all the attributes in this population, which is very likely to receive the treatment from all we see. So that's an propensity score column. You can get that from sklearn. You make a machine learning model and predict the probability of receiving treatment.
You can say any kind of model.
Yeah, any kind of model you want, logistic regression, some crazy machine learning, whatever, it doesn't really matter.
Take the treatment from the covariance.
Predict the treatment from the covariance. Yeah. They're like very similar in their attributes. And so we think that we control for these attributes. They might have similar age, they might have similar income, they might have similar jobs, whatever it is. And likewise, these 2 and 4 here have very similar propensity scores predicted, and they have a difference in treatment. And the idea is, if you calculate these propensity scores and match on them, you're making groups of people that are like very similar in their attributes except for the treatment. So eventually you get something like this where I just pull together the people that are matched, and I can say that they're like very similar in their attributes except for the treatment. And now I control for these covariates in essence, and I can calculate the average treatment effect, which is just, you can see the formula down here. So essentially, like the outcome, the average of the outcome among the treatment group and the average of the outcome can be not 3 degrees, and the difference is showing up. And that absolute difference is 7.5. And I would interpret that as if I accounted for all the relevant confounders in the covariate list, this is the causal effect of that treatment variable. You wouldn't want to include colliders and mediators in that list of covariates, just confounders. Identify confounders, run a propensity score model on it, generate propensity scores, match the people that are similar, and then calculate that absolute difference. And whatever this is, accounting for all the confounders, I can say the causal effect to the best of my ability is 7.5. Which is very different from what I would see in raw data. I didn't account for confounders and sort of, and then after that, and said, hey, what's the average, what's the mean of the treatment group and not treated group, and what's the delta there? It would be way different. So in this next notebook,
Hey, one quick question.
Yeah.
How is that different in chat values?
So the difference here is sort of the domain knowledge piece. By incorporating just what I consider to be confounders and controlling for the right thing. And chat values they're more sort of like correlative. It's this variable is like a strong predictor of the outcome, but it's not, there's no distinction between this confounder, collider, that sort of thing.
If I incorporated the mass knowledge into those chat values, it would theoretically be very similar.
I don't know if that's true. Like, you wouldn't account for like temporality between things necessarily.
Oh, I don't know, I'm just asking.
Yeah. Well, I think with chat value calculations, like you haven't ensured that you have a temporality assumption that the treatment occurs before we get that. I think it's just a different set of methods where it's not a different set, yeah. So, in this notebook here, what you're going to do is use a really well-known data set called the Roni data set, which I think was a way of sort of understanding the effect of the job training program on eventual earnings.
We go to, we go to.
Oh, whoops. Sorry. So yeah, we're going to get a data set that looks like this. It's a pandas data frame. It's a really classic. Right, classic data set, job training program, and its relationship with income down the road. And we're going to apply propensity score matching. We're going to apply propensity score matching to understand the sort of adjusted, unconfounded relationship between job training and income down the road. So we're going to select your covariates and your variables of interest. We're going to take a look at what the raw treatment effect is, which is like if I just look at people that are treated, that receive the job training or data set without controlling for anything, what is their average income down the road and the difference between how much you receive that job training, and just find a number. And then we'll apply propensity score matching and see how that number changes. And we'll get rid of the delta there, which means some control for the variables.